In this video, we're going to talk about peak shapes. Now, we've said that we can think of our diffraction pattern as a background with some sort of peak sitting on it. And when mathematically the program is doing its calculation of that diffraction pattern, it's obviously going to need some sort of function to define the particular shape of the peaks that it's putting in the diffraction pattern. So, and fit those and use those to fit the data. So what we're going to think about in this video are some of the common peak shapes that we might come across during diffraction analysis. So the first two peak shapes that it's worth considering or being aware of are the Gaussian and Lorentzian peak shapes. Now I've got them shown here. So on the left I've got the mathematical equation for the Gaussian, which is also the normal distribution. And you can see on the graph that's shown here in blue, that's shown here in blue on the graph, this Gaussian peak here. So just to point out, mathematically, we've got these terms A, B, and C in here, which are going to relate to things like the peak intensity, the peak position, and the peak width. It's worth noting that A will, in this case, depend on the exact normalization, and you may need to be careful with the normalization for the exact area. A is not in itself the area. It will also depend on some other things, but it depends on the exact normalization you're using. But in general, what we can think about is that our Gaussian peak, we can say we've got a peak position, we've got a peak intensity, and we've got a peak width. And you can see that this Gaussian peak is quite sort of pointy in shape and has some tails, but not sort of very large tails coming out here. By contrast, the Lorentzian, shown here in red, and with the equation shown over here on the right, you can see has much longer tails that come out on either side of it. And it's defined by this equation here. And again, notice we've got a peak intensity term, we've got a peak position term, and we've got a peak gamma term within this expression. So these are two common peak shapes, and they come from probability theory and are often used in probability theory to describe various distributions and things. But they're quite useful peak shapes to use. In fact, when we come to diffraction analysis, one of the most common peak shapes that you'll come across is actually something called a pseudo-void. And what a pseudo-void is, and I've put the equation up here, is it's a combination of the Lorentzian and the Gaussian that we just defined on the previous slide. So it's just a mathematical sum of these two with some sort of weighting. So you can see here in this expression I've got this eta term which weights them. So if eta were to equal 1, it would be entirely Gaussian. If eta were to equal 1, this term would be equal, the Lorentzian would disappear. But if eta equals 0, then the Lorentzian is there on its own, and we lose the Gaussian term in this. So the pseudo-void, it turns out, is actually a really good model for the peak shape that you'll get in a diffraction experiment. And it tends to be the most common peak shape that we use, or one of the most common peak shapes that we use in diffraction refinement. So it's really worth being aware of it. And it's worth just being aware that therefore that peak overall, when we've defined it, will have some sort of position associated with it, some sort of area, which will be done by scaling, and also some sort of width. And actually the width will therefore be controlled. We've got a Gaussian width and a Lorentzian width term in this. We'll have to consider the width of those two separate components of that function and how we vary the two. And actually when we come on to talking about peak widths later, you'll see that there are some terms that are related to the Lorentzian term and some that are related to the Gaussian term that we'll use within our refinement. So this is the pseudo-void, which, as I say, is one of the most common. You might be asking yourself, why is it a pseudo-void and not a void? Well, there is actually a void function as well. And the void function mathematically is a convolution of a Gaussian and a Lorentzian. So rather than our pseudo-void, which was the sum, the actual full void is going to be a convolution of the two. And computationally, doing a convolution is much more computationally expensive than doing an addition. And actually, people have found that a pseudo-void actually is a very good peak shape for modeling these things and is not too computationally expensive. So it tends to be the sort of preferred peak shape of choice when we're doing diffraction refinement. Now, normally when we set up a refinement, what we have to do is we have to define that peak shape at the beginning of the refinement process. And so different softwares will have different peak shapes loaded into them that you can choose. And it's worth being aware of what software you're using and what peak shape function it is using, and whether that's suitable or appropriate for the type of refinement you're doing. As I say, the pseudo-voids that we've shown here are very good for things like lab diffractometers and often capture the shape of those peaks quite well. However, sometimes you'll need to use adapted forms of these peak shapes as well. So for example, if you're doing a neutron experiment, in neutron experiments often our neutrons pass through a moderator, and these actually create a strong asymmetry to the peak, which then has to be modelled. And so then we use things like back-to-back exponentials convoluted with pseudo-voids in order to create a good peak shape. So very often if you're doing one of these experiments and you want to know what peak shape would be suitable, it's worth speaking to people who use the instrument regularly, instrument scientists at Beamline facilities or technicians in the lab, or just other users, to find out what type of peak shape they're using in their refinement to capture it. And then generally what we'll do is we'll do a calibration where we can use a known standard in order to work out what that peak shape should be and the ideal parameters that we need in order to describe the ideal peak shape produced by the instrument that we're using. So this peak shape is going to be controlled by our setup and by the instrument that we're using. So as I say, it's worth thinking about just in a little detail and defining it at the beginning. So now what we've seen is, having defined this peak shape, we're then going to go about refining the various parameters within that peak shape in order to get our peaks to match up with the observed peaks in the diffraction pattern. And those things are the position, the intensity, and the width. So we're going to now think about these each in turn in more detail and the various physical parameters that relate to each of those terms.